right? At the same time, Y30, at the other end of Y30, right? This will be known as your X30 point. Okay, that will be your X30 point, right? Because usually if one end is Y, the other end is what? X, right? So for this case, your normal stress X30 will be equal to -5. And because it's going towards the right hand side, right? Because from the center of the circle, it's going towards the right hand side. The formula will still be the same, except this will be a plus. Okay, 4.509. So this will be equal to -5 plus by 5 plus 4.509. So you get minus 0.491 megapascal. My drawing is a bit off. Okay, so -5 plus by 4.509 is going minus 4 point. Okay, so if I were to draw this accurately, okay, if I were to draw this accurately without a compass or a protractor where this point is, so it's going to be both are in a minus. Okay, so one is minus 0.4. Okay, so 0 points here, so it will be about here. Okay, so this point over here is going to be your Y30 point, and this point over here will be your X30 point. Okay, how I know that? Because now I know the actual value, right? So now we're going to construct Moser. We're going. So we seen the element now. Okay, so we have seen the location on Mohr circle. We are going back to the element to construct the element. Okay, so now it's going to be 30 degrees. So we're going to construct the element, bring it back to the element stage. So we have our 0, 0, right? This is our 0, 0. Then it's going to rotate clockwise by 30 degrees. So I'm just going to be going to guesstimate that this is 30 degrees. Okay, so this is my 30 degrees orientation. Okay. All right, so this is my 30 degrees orientation clockwise. And then I'm going to copy this. Wrong thing. Apologies. Right. Then we're going to draw an element based on this orientation. Okay, we're going to sketch the element out. So when we sketch our element, we know this line, right? This horizontal line, this used to be our Y, right? And now this point over here, right? This plane over here, this is our Y30, right? And the vertical plane over here, this used to be our, or this is our X, right? And now this is our what? X30, right? So you note Y30 to X30 is 90 degrees. That is why, right? If you look at the Mohr circle, Y30 and X30 is what? 180 degrees, okay? So from here, you look at your Y to Y30. So the value we calculated that Y30 will be minus 9.509. So you'll be coming under compression. So it'll be minus 9, or you just draw the arrow down. So it's known as compression, 9.509 megapascal. And then the other side, okay, X30, which is this point over here, right? So you have also compression, and it's going at 0.491 megapascal. And then we don't forget our shear, right? We have a shear of 37.811. Okay. So if you look at 37, so if you look at Y30, right? So Y30, the element is going to rotate what? Clockwise. Okay. So if you look at here Y30, the element is going to rotate what direction? The element will rotate clockwise. So in order for the element to rotate clockwise on Y30, so let's focus on Y30 line. Okay, so this is our Y30 line. Let's focus on. So for the element to go clockwise, the shear has to go which direction? Down direction. Yes or no? Right? The shear has to go that right. So this shear will be equal to 37.811 megapascal. Right? So let's look at X now. Okay, so X, the element has to go anti-clockwise, right? So we're going to focus on this surface over here, right? So if you look at the surface over there, it has to go clockwise. The shear has to be in this direction. Okay. So that's how you draw your element rotated 30 degrees, okay, from the original stress state from here by 30 degrees. So far, anyone, any questions so far? Are we okay? Is the rotation, okay? The shear, usually students are confused, right? Are you all clear now or no? We're okay? So no question, no reply. I'm going to assume it to be okay. If you're not okay, you can type a message, okay? I'll read your message if you're not okay with it, and I'll critically read your message. Right. So some of you might ask, Eugene, can I now deal with, let's say if I want to rotate from my X. Okay, you decide that, hey, I want to rotate. Yes, you can. The answer will be the same. How? So if you rotate from your X, right? So the angle will be X what? X 60. Right? Because this angle over here, theta will be equal to what? 60 degrees. Right? And 60 degrees will be in what direction? If you look at there, 60 degrees will be anti-clockwise. Yes or no? So now you go into this angle over here. So from point X now, right, you rotate 60 degree, 120. So you will rotate 120 degrees anti-clockwise, right? Why anti-clockwise? Because this is going anti-clockwise. So this will be equal to 120 degrees also. So now you are going to label this point now as what? X what? X 60. The answer will be the same. Okay, and then over the other side will be your Y what? 60. The answer will be absolutely be the what? Be the same. Okay, because they all ended up where? They all end up at the same point. So do not be afraid to rotate from either the intersecting Y plane or the intersecting X plane. Okay, the answer will be the what? Will be the same. Okay, any questions so far? So now all of you are capable of going from element to Mohr circle, and then Mohr circle, bring it back to the element. Okay, now there's another term that I want to elaborate. Okay, there's another term that I'd like to elaborate is in plane. Okay, you guys will see quite a lot of this. Okay, is the in plane. So what is in plane and out of plane? Okay, so you'll see this term quite often in your textbook. They say, hey, find the shear stress, the in-plane shear stress, or the out-plane shear stress. So I'll show you what does this mean. So it usually has to do with a cube, okay, or a 3D element. I'm not going to do 3D yet. I'm just going to introduce to you what do we mean by in-plane and what do we mean by out-plane. Okay, so if we look at 3D, I'm going to draw 3D now. Okay, so this is our transformation. Oh, yeah, I'm going to draw our element first. Okay, so this is our element. I'm going to stop short here. So this is our 3D element, right? Right. Then I'm going to draw our transformation. So this is X, Y, and this is our Z. Okay. So we know that this plane over here is our YZ plane. This plane over here is your XZ plane. And the plane over here is your YZ, is your XY plane. So by observation, okay, we will call this, by observation, we will call this in plane. And the other two will be out of plane. Okay, the other two will be out of plane. Now I'm going to draw the same element but oriented in a different way now. Okay, so now again the transformation is the same. So this is X, Y, and Z. Oops, sorry. So this is my Z. So now I'm going to draw this way now. I'm going to draw the element doing this now. Okay, so this is our element now. So now our element is oriented in this way. Okay, then we have right. So now still the same thing. So this is still our XY plane. This will be our YZ plane. And this will be our XZ plane. So for this case, right, for this case, what we have drawn now the XZ plane is in plane. And the XY plane is out of plane. And the YZ is out of plane. Okay. So question to any one of you, when is it in plane and when is it out of plane? Anyone, please. Anyone? When do we classify something as in plane and some? So we have two very different situations. So when is it an in plane and when is it an out plane? Anyone, please.
The plane with the largest area is in plane.
I like that. Okay, there you go. Okay, so I like that. So the area, well done. Okay, so the plane with the largest surface area is the in plane. Right. So you can see that of both orientation, the larger surface area, we always classify them as in plane. Okay, the smaller surface area classify out plane. Hey, I've been trying to look for this from textbook and no textbook tells me about it. Okay, so I'm telling you, textbook assume that this is understood. Everyone should know about it. Not true.